everyone, in this and the next few sections, we will introduce several results on fixed points. To keep our discussion simple, we will only look at real-valued one-dimensional functions which send closed interval AB into itself. That being said, most results and methods developed here will be readily adapted to a more general setting. To start with, let us introduce the definition of a fixed point. Assume that f is a function from the closed interval AB into itself. We say a point x star is a fixed point under f if fx star is equal to x star precisely. In other words, the point x star is not moved under the action of f. That's why we call it a fixed point. For example, consider the function f from the closed interval 0, 1 into itself, where x is mapped to x squared. Solving the equation fx is equal to x, that is, x squared is equal to x, we obtain that x is either 0 or 1. That means f has two fixed points, namely 0 and 1. Geometrically, you can see that each fixed point corresponds to an intersection of the function graph and the straight line y is equal to x. Now, a natural question arises immediately. Given an arbitrary function f from AB into itself, do fixed points always exist? In the rest of this section, we provide a confirmative answer to this question under some mild assumption on continuity. More precisely speaking, we have the Brouwer fixed point theorem, which claims that any continuous function f from the closed interval AB into itself has at least one fixed point. How do we prove this? Well, notice that since f is a function which sends AB into itself, we must have fa is greater than or equal to a, and fb is less than or equal to b. Let us distinguish two scenarios. First, if either fa is indeed equal to a or fb is equal to b, we are done. Because in the former case, a is a fixed point, while in the latter case, b is a fixed point. Now, what if we're in the second scenario, where neither fa is equal to a, nor fb is equal to b? Well, if that is the case, let us consider a new function h from the closed interval ab to R, where x is mapped to x minus fx. Clearly, h is also a continuous function on ab. Now, observe that if fa is not equal to a, it must be strictly greater than a. Similarly, if fb is not equal to b, it must be strictly less than b. So now in this scenario, ha is negative, while hb is positive. Now recall h is continuous on ab. Applying the intermediate value theorem leads to a point c between a and b, such that hc is equal to 0, which means precisely that c is equal to fc. In other words, c is a desired fixed point. That finishes the proof. You see, this theorem is very useful, because not every function from AB to AB permits a simple and explicit formula as our previous example. For example, if you look at the following function, it is not evident how can we solve the equation fx is equal to x in order to find x. However, since a function is still continuous from 0, 1 to 0, 1, the Brouwer fixed point theorem guarantees at least the existence of a fixed point. Several remarks for the theorem. Number 1, the condition on continuity cannot be dropped. To see this, simply consider the following counterexample f from -1 and 1 into itself, where all the non-zero numbers are mapped to 0, while 0 itself is mapped to 1. Clearly, nobody is mapped to itself, and a fixed point does not exist in this case. The reason is precisely due to the discontinuity of this function at 0. Next, although the theorem guarantees the existence of the fixed point, it doesn't give us the uniqueness of the fixed point. To see this, simply recall our previous example where f is a function from 0, 1 to 0, 1, with x being sent to x squared. Although this is indeed a continuous function, we have actually two fixed points, at 0 and 1 respectively. To see a more radical example, let us consider a function f from -1 to 1, where x is sent to itself, This is clearly a continuous function as well, but this time, each point in the domain is a fixed point of its own right. In other words, we have infinitely many fixed points. Last but not least, even if the fixed point is unique, it is not clear whether this fixed point can be approached by function iterations. For example, consider the function f from -1 to 1 where x is mapped to -x. We see that this function is continuous with a unique fixed point at 0. Now, if we start our initial value at any point other than 0, say 1/2, then the sequence produced by the function iteration will be an oscillating sequence. Such will never converge to the fixed point 0. Of course, despite these drawbacks, the Brouwer fixed point theorem is still a powerful tool to guarantee the existence of fixed points in a qualitative way. And perhaps we should not be that greedy. After all, we did not impose any strong condition other than the continuity. In the next section, we will upgrade the continuous functions to contracting ones and introduce the Banach fixed point theorem.